It is.
You guys officially graduated the senior VP or
All we do, so most of our job is done. We sort of enjoy writing.
Hello, everyone.
So we think.
It's a great pleasure to have Professor Zhang for the colloquium today. I got to know Bing, I don't know, like many years ago. So when Bing was a PhD student at Beijing University, and at that time I was an undergraduate. And in fact, my very first scientific paper was with Bing. Bing's research field focuses on all types of phenomena related to high energy astrophysics. So after he obtained his PhD from Beijing University, he went to NASA Goddard Space Center as a postdoc and working on neutron stars and pulsars. And later he went to Penn State University where he switched his research field to gamma ray burst. And now Bing Zhang is a professor at the University of Nevada at Las Vegas. And today he's going to share his view on a new discovery, very exciting discovery of a new type of phenomena in the universe.
First, I'd like to thank my very good friend Zhang for the invitation, and I'm glad to come back again. I came to University of Utah maybe 8 years ago, and it's quite different now. There's a huge expansion in the astronomy group, and I'm very happy to visit the group and discuss with the faculty, students there. And thank you all for coming to this talk. So the subject is fast radio bursts. So what are fast radio bursts? They are FRBs. So for many years, I have been working on GRBs, which is gamma ray bursts. And now something new was discovered. You just replace G by one letter before F, and we become very excited. Hopefully keep us busy so we don't lose jobs. So hopefully in the future we have ERB, for example, DRB. Keep working on this. Okay, so what are these guys? So they were first discovered pretty recently in 2007. At that time, Duncan Lorimer discovered the first case. Just one case, and not many people seriously believe that they are true astronomical events. And right now, still a lot of people doubt about it. But then in 2013, Thornton et al., they published a paper in Science, and they discovered 4 more. So these are 4 more. So you can see there are radio pulses. If you look at the duration, it's about milliseconds. And only one pulse. So only one pulse. There's no significant variability. So I have been working on GRBs many years. If you look at the GRB light curves, you have very high variability, many spikes. And this is just one pulse. And they happen at high galactic latitudes, which means they're not concentrated on this galactic plane, probably not from our Milky Way galaxy. And anomalously high dispersion measure, this is called DM. I'll talk about this a little bit more later. It's just basically saying that the pulses at different frequencies arrive at different times. And this tells us how many free electrons along the line of sight. We have too many electrons to be within the galaxy. So we have to consider the electrons in the universe. And if that is the case, then the redshift, which means tells you the distance from us, is from 0.5 to 1, which means these guys probably are cosmological. if we believe that distance, then peak radial luminosity is 10 to 43 ergs per second. So this one, compared with gamma ray bursts that I have been working on, it's very weak. It's for GRBs, we are talking about 52, 53, almost 10 orders magnitude brighter. Compared with our sun, however, this is pretty large. Our solar luminosity is probably 10 orders magnitude lower, 10 to 33 ergs per second. The total emission in this one pulse is about 10 to the 40 ergs. And the event rate is very, very high, which means it happens very often if we believe that they're all in the cosmological distances. So every year, every galaxy, there's 10 to minus 3, which means if we watch our Milky Way galaxy for 1,000 years, then we should be see one. Of course, in our lifetime, we probably won't see one in our galaxy. However, we have so many galaxies in the universe, and we see these guys very often. So all sky, every day, you see quite a lot, thousands of these guys. And no electromagnetic counterparts in other wavelengths. So usually, for gamma ray bursts, for example, you can see it in X-rays and optical, but here it's just in radio, so we don't have other counterparts. Here's a little bit more about this burst. So you can see this is the frequency, this is the arrival time. So for one pulse, you can see it arrives at different times. And this delay is so-called DM, dispersion measure. It is related to the number density of free electrons along the line of sight. So if you integrate over distance, you get this so-called DM. And then these are the measured DM values. They're too large as compared to our galactic values. So this is in our galaxy. These are so-called radio pulsars. For each radio pulsar, you have the DM. That is the free electron along the line of sight for those neutron stars. And they are very low at these high galactic latitudes. And these guys are way above that, which means they are not inside galaxy. If they are inside the galaxy, their DM should be this high, but they're way higher than that. Okay. Models proposed so far, there are a bunch. For example, collapses of supermassive neutron stars to black holes. I'll talk about this a little bit later. Magnetosphere interaction during neutron star mergers. We have two neutron stars at the final stage of their merging process. They lose gravitational wave and they're getting closer and closer. Eventually they will smash together. And people said, okay, so these guys can make radio bursts. Merger of two white dwarfs. If we have two white dwarfs, one can also probably do this. Magnetar radio bursts. So magnetars are the galactic neutron stars with extremely high magnetic fields, and we see these guys in our galaxy. And when they make bursts, then people say, okay, they will probably make radio bursts as well. Evaporation of primordial black holes. So some theorists said, okay, we will form black holes with all different masses from the very beginning of the universe, and they keep evaporating following Hawking's theory. And some of them are evaporating right now. And these are the candidates to produce FRBs. Flaring stars. So this is the weird model. So we have a star somehow in the magnetosphere makes such kind of bursts. And probably just local events, not actual physical origin at all. So this is Kulkarni et al. Paper, which Zhang is one of the co-authors. Of course, they also propose, for example, this model. There are other things. Today at lunch, I learned from Zhang that there's a scenario called cosmic string. Yes,
So are the flaring stars, is that galactic or are those extragalactic?
They are talking about the galactic one. So that is a problem. If they're galactic, why they're all at high galactic latitudes?
And with a high dispersion.
Right. So they look at the error boxes of these guys and found that one of them, there's nearby star, and they claim that probably they are all from there. I'll criticize these models a little bit later. Lessons from GRBs. So for gamma ray bursts, because I have been working on this for many years. They were discovered in the 1960s. At that time, nobody knows where they come from, and there were more than 100 models at that time. So according to this paper, they collected 112 models. And then at that time, the bursts probably only tens of dozen maybe. So the number of the models greatly exceeded the number of bursts. And turned out that only 2 of those 112 models turned out to be correct. So these current models, massive star collapses and compact star mergers. So the successful rate for theories is less than 2%. So you can say, oh, these are theories heaven or hell. So you can publish a lot of papers, but eventually turned out to be wrong. Okay, how about FRBs? I would predict probably more than 10 models. Right now it's already more than 10 models, less than 100. That's because we have more physical constraints, and we also, people already learned the lessons. You don't publish those junk papers. However, who knows? So there's theories, they have all kinds of crazy ideas. So right now, the number of models is already exceeds the number of bursts, so that's for sure. Challenge to theorists. Can we get the correct one? So this is the big challenge. So I always ask myself, should I publish a paper which turns out to be wrong? Starting from scratch, let's forget about what people told us already. Let's just look at the data. The duration, milliseconds. Only 1 pulse. This already told us a lot of things. Milliseconds, so in astrophysics, we usually use this to estimate the size of the emission region. C times delta T, it turns out to be 10 to the 7, 10 to 8 centimeters. So this is a very small region. And only neutron stars and black holes probably fit into this scenario. White dwarfs can do it, but the size of the white dwarf is already 10 to 9 centimeters. They have to, some people claim this, they have to really claim that the local region, probably the polar cap of some white dwarf is doing this. And just 1 pulse, so this is very different from the gamma burst. Gamma burst we know probably is newborn black hole. There's an accretion going on, so they have high variability. And here, just 1 pulse probably is just 1 event. So its engine variability is not significant. So probably just once a lifetime. High galactic latitudes, anomalous high DM. I already talked about this. So it should be extragalactic cosmological origin. Of course, I will argue that could be from the flaring star. However, in history, we have 3 debates: galactic versus extragalactic. For example, galaxies, quasars, and GRBs. They are all debates for many years, and turned out every time the extragalactic one won. Okay, I'm not saying that we should just based on this we claim that, but if we have to bet some money on it, I probably will bet on this extragalactic model. High event rate. So this is a little bit worrisome. So it must involve some very common phenomena. So this is something any model has to solve. No electromagnetic counterparts. Here, I don't worry too much. Probably they don't have counterparts. Probably they just have counterparts we didn't detect, because these guys are very, very short events. And then if we don't have the right telescope watching at the same direction at the right time, we probably won't see other emission.
How well localized are they on the sky?
Square degrees. So within the field of view, actually, there have a lot of galaxies. So you really cannot see. It's just similar to GRBs in the very early era. So you cannot see where it comes from. Issues of the other models, and also in Zhang's paper, also criticized. So I'll criticize these models. If it's double neutron star mergers, it comes from outside. So 2 neutron stars come from outside and squeeze in to make these radio pulses. These radio pulses, they are very bright. They have to be coherent. So what is coherent, which means if you add the emission power from individual electrons, if you add together, you cannot reach that brightness. You have to make all these electrons to radiate coherently, similar like to some antenna or some laser, for example. So if something smashed together, it's a very messy process. I will see some shocks, but definitely not very organized emission like this. So that's something I don't like that model. Mergers of binary white dwarfs. Time scale may be too long because white dwarfs they're large. They have to invoke very small regions, but why? Magnetar radio bursts, and probably this is an attractive proposal, but why no gamma rays? And you can say they're too far away. However, we already saw a lot of gamma rays in this magnetar burst in our galaxy. Why you didn't see very bright radio signal? That is something. But this model probably, in my opinion, is second best. Evaporation of primordial black holes. So this one is opposite, because when you evaporate, the black hole size becomes smaller, smaller. The temperature goes higher and higher. So you're supposed to give a bright gamma ray burst, not a radio burst. So this has to be this has been a short GRB model. So now people want to revise it to make a radio burst. Flaring stars, a lot of issues. Why high galactic latitude, time scale too short, and free absorption limit. So I don't want to go into details. Then this is my favorite model. So this is basically saying that, okay, we have a neutron star, and this neutron star should not be there if it is not spinning at all. The total mass already exceeded the maximum mass allowed by a neutron star. But it is still a neutron star because it is spinning very, very rapidly. So this centrifugal force is supporting this star. But it is gradually slowing down, and eventually you lose this centrifugal support, and then, boom, you collapse and make a black hole. So within this scenario, it has inwards out. So when you collapse into a black hole, because black hole, there's no Hare theorem. So you can have mass, spin, you can have charge, but you cannot have magnetic field. Okay? And this neutron star carries the magnetosphere. During this formation of the black hole, the bulk of the neutron star will fall into the black hole. However, the magnetosphere has to be somehow ejected. During this ejection, it's similar to the radio pulsars. We know there's a magnetosphere and there's a spark from the bottom, and then we know radio pulsars are making radio pulses. So this probably will make a radio pulse this way. And this was not my original proposal. This was a proposal by Helk and Razzola, but they were invoking such kind of collapses for much longer delays. So they're saying that this supermassive neutron star, they will survive for thousands of years or million years, and gradually they slow down and boom, make a black hole and FRB. And my contribution to this is, okay, if this scenario is correct, then one should also expect some of them happen very, very shortly. So if these supermassive neutron stars were made from some huge supernova explosion associated with gamma ray bursts, initially they are spinning very, very rapidly. Because their B field is also high, then quickly they will spin down within hundreds of seconds, for minutes to days, they can collapse. So if that is the case, one should be able to see an FRB associated with a gamma ray burst. So that was my proposal. So GRB, the gamma ray burst, so there are two types, central engines. So in the middle, it can be a black hole, accreting black hole, or can be a magnetar, rapidly spinning down, highly magnetized millisecond magnetar. So there have been discussion for many years. Actually, within the GRB field, we don't know which one is the case. However, we did see some smoking gun type of the phenomena. So these are the light curves of gamma ray burst afterglow. So quickly say a few words. Gamma ray bursts, they are just bursting gamma rays. And after the burst of gamma rays, if you use X-ray telescope and optical telescope, look in that direction, you will see a fading afterglow. And usually these fading afterglow has a power law decay, like this optical decay should be power, this optical should be power law decay. However, very occasionally, rarely, you see something like this. So this is X-ray afterglow. Usually X-ray goes down. But this one you have a plateau, keep the same sort of flux and stay for 10,000 seconds, and suddenly you drop like a stone. So such kind of behavior, and this one too, has been a challenge to the GRB theories. So we have had trouble to interpret those guys. But there was one scenario which can interpret that is, okay, so this comes from a magnetar. So this emission is not from the external shock, it's just a spinning down neutron, supermassive neutron star. And then during the spin down, it will give you an X-ray emission. And this X-ray emission has a constant luminosity. And suddenly, it disappeared. Where did it go? It goes to a black hole. Suddenly it disappears, so that's why you have a huge drop of the flux. So such kind of phenomena actually have been observed in the GRBs, and we already used that scenario, supermassive neutron star collapsing into a black hole, to interpret it. And these internal plateaus, initially they were discovered after long GRBs. Long GRBs are believed to be the collapses of massive stars. However, in some short GRBs are believed to be mergers of two neutron stars, double neutron stars. And actually, a lot of these double neutron merger GRBs also have this plateau. So you can see the X-ray looks like flat. You can say, okay, it didn't extend too long, but look at this is log scale. I didn't put the sticks here. So it's log scale, so which means this is actually pretty long. Then you suddenly drop. Okay. So this again tells you double neutron star merger probably make a heavy neutron star and stay around for a while, and then collapse into a black hole. And these are the other short GRBs. A lot of short GRBs show such kind of behavior. So what I proposed in this paper was that, okay, probably we do have some GRBs, both long and short, have such kind of supermassive neutron star central engine. And at the end of this plateau means steady emission and suddenly drop. At this time, that is when the supermassive neutron star collapses into a black hole. And when that happens, magnetic hair is ejected, and you make a radio burst. So this is where we predict there should be a FRB. Some of them, you can see clear signature like this. Some of them have a more smoother signature. So this can be, I don't want to go into detail. So this is from the external shock. So this one is the internal emission. This we really see the magnetar emission. This is indirectly, we probably see it magnetar emission, but we are not sure whether it is here or the collapse to a black hole. We don't know whether here or here. But anyway, so we should probably see an FRB there. Okay, how to generate an FRB within this scenario? So I said, okay, we have a supermassive neutron star collapsing in the black hole. How do you produce radio emission? No one knows. Why no one knows? Well, because no one knows how pulsars work after 40 years. What we know is we have to invoke a coherent mechanism. I just said it is so bright, it must be coherent. And coherent, there are two mechanisms. One is like an antenna, like a bunch of mechanisms. So you make many particles to radiate together, so that your power, instead of it's just the power of in the particle multiplied by n, is multiplied by n squared. So in that way you can increase your flux tremendously. Another is a maser, so it's basically absorption, but it's negative absorption, basically amplifying your radio waves more and more. So we know these two mechanisms. However, radio pulsars have been studied for 40 years. Thousands of radio pulsars have been discovered. However, we don't know how what is making it. So here we don't really want to propose a model for radio emission, but what I'm saying is it's very similar to radio pulsars. We have magnetosphere, we have something from the bottom. For the radio pulsar, we have a spark near the bottom, and here we just eject the magnetosphere, and then particles start to do whatever pulsars are doing. Okay, but how to test this scenario? So we need to invoke the multi-wavelength campaign. So we can go two directions. One is from GRBs to FRBs. The event rate of FRBs is much higher than GRBs. It's 1,000 times higher, which means if you look at an FRB and try to look for GRB, you won't find any. You have to search for 1,000 of them in order to get one. However, the other way, if you see a GRB and go after to look for FRB, the fraction is much higher. It's just to see what fraction of GRBs has this supermassive central engine, and it's about half. We had a statistical work recently. So my suggestion is, okay, let's just follow up all the GRBs with radio telescope and go to the GRB very quickly within hundreds of seconds, and then see what happens. However, the problem is radio telescopes, they're heavy, they're big. It's not really easy to slew over within hundreds of seconds. You can come over maybe half a day, couple hours. Then if this supermassive neutron star stay long enough, you probably will catch the pulse. Or it's already collapsed into a black hole, then you miss it. So that is the challenge. In order to do this, you probably cannot use VLA, very big radio telescope. You have to use a very small but very fast radio telescope to do this. Then the question is, how about the other FRBs? Only 1 out of 1,000 FRBs are probably associated with GRBs. And how about the other 999? Those guys, there are two possible scenarios. One is, okay, they are also associated with these guys, but we didn't see the jet direction. We are looking at other directions. In this case, we only see FRB, but we don't see the GRB. However, this has a problem because both long and short GRBs, we have a lot of material in the equatorial directions. And the radio wave coming from the center cannot penetrate through this. For long GRBs, it's hopeless. For short GRBs, probably because you eject some material, but probably not fully cover the full high sky. There are some holes. If that's the case, probably you will see a FRB for a certain fraction of merger events. But in any case, the event rate is not high enough. So we have to introduce other mechanisms. But still the same model. It's still this supermassive neutron star collapsing into a black hole, but there's a distribution of delay times, right? So most of them, the delay time can be thousands of years, millions of years. So this was the original proposal by Felk and Rizzola. What I'm saying is only a small fraction, a tail of that distribution goes to very early, and then we can catch them after GRBs. So these are numbers. From FRB to GRBs, 1 out of 1,000. From GRBs to FRBs, 1 out of 2. So we try to detect FRBs following GRBs, not the other way around. Okay, so far, just wild imaginations. When I first wrote this paper, I was saying, I just give it a bet. Maybe it turns out to be those 98% wrong papers. Then after I posted the first paper on the archive, one friend of mine wrote to me, "Did you notice this paper?" I said, "No." And I read their paper. It's Banista et al. They already published 1 year before my paper. Actually, this was before the Thornton et al. Paper. What they did was exactly the same thing I just mentioned. They tried to use a very small radio telescope, a 12-meter telescope, and to follow some GRBs. And then they searched for dispersed radio pulses. They just did it for no reason. They said, okay, what if I want something? And their title actually is saying that the upper limits of this dispersed signal. So they didn't believe they detected anything. They said, okay, I didn't detect anything, and this is my upper limit. However, that was probably why I missed the paper, because I said, okay, upper limit, who cares about upper limits? But now, my friends told me, look at this paper, and I look at, okay, actually they reported 2 plausible detections. So look at these 2. So these are the radio signal. You can see there's a spike there. This one is more significant, okay? And then they claim this one is 6.2 sigma, this one is 6.6 sigma. So it's 6 sigma detection. In other fields, 6 sigma is already pretty high. And in radio pulsar, 6 sigma not very significant. So that's why they were cautious. But what makes this thing very interesting is where these pulses happen. So these are X-ray light curves. As I showed you earlier, there was a prediction. I said there's a plateau, and the plateau, that is where the FRB is supposed to happen. Look at this one. There's a plateau there, and there's a flare that can be the magnetar did something. And at the end of the flare, boom, there's FRB happens. So this one is quite, even though their paper published before mine, I would say mine is prediction, and this one is. But look at it. So why it is a prediction? Because this one satisfied, the other one didn't satisfy. So if I saw this paper earlier, I would say, okay, I predict here and also there. I didn't do that. But anyway, so this one is very good. It's consistent with the prediction. So it's at the end of the plateau. This one is puzzling. This is plateau, and then it is after this, and then there's another break. But this break can be the transition from internal magnetar emission to external shock. But there's nothing special there. It's just a comparison between the external shock and the internal emission. But it does not rule out what I said. It is consistent with the picture, because the magnetar can spin down to this level and then keep spinning down as T2 minus 2 and then collapse at some unspecified time. So this one can be also understood within that picture, even though it's not a prediction. Okay, so with this one, it's no longer just a wild imagination. It could be a real case. So right now, I know the Australians, they're trying to search for more, and myself is also collaborating with people to search for more, and just to get a not too big telescope as long as it can through quickly. Let's try to see whether we have more. Okay, the rest of the talk is based on this assumption. Okay, if this FRB-GRB association is established, okay, so right now I'm just saying this looks like plausible, but who knows, maybe it turns out to be wrong. But if these associations are correct, then what is this? What is this? Yeah, so this is kill 2 birds with 1 stone, but in Chinese it is kill 2 vultures with 1 arrow. So this is Chinese character. So somehow it's basically the same meaning. And there's no kill in Chinese. So this is 1, this is 2, this is vulture, this is arrow. So 1 arrow, 2 vultures. Why is that? Because we don't know FRBs, we don't know GRBs. FRBs, I said there are more than 10 models. We don't know which one is correct. For GRBs, we don't know whether the central engine is a neutron star or a black hole. However, if we see such kind of associations in the future, then we can solve these 2 problems simultaneously, because for FRBs, at least some FRBs has to be this supermassive neutron star collapsed into black holes. So we find a energy source or central engine of FRBs. And for GRBs, we can say, okay, at least some GRBs have this millisecond magnetar central engine rather than a black hole. So this is a very big step in both fields, especially if FRB field. So that's why searching for such kind of associations are extremely important. Beyond that, probably we can kill the 3rd vulture. Probably one can use data to determine maximum mass of neutron stars, and then constrain the equational state of nuclear matter. So this is a huge physics problem in the field of nuclear physics. So this is the neutron star equation of state plot. So this is the radius, and this is the mass. And there are so many different models. So which means for a neutron star at this mass, one should have this mass should have this radius. And uncertainty comes from the core, because the density there is very high, extremely high. We don't know whether it makes some pion condensation or makes some quarks, quark gluon plasma. There are extreme models called strange quark models. They are saying the entire neutron star is not made of neutrons. They are a huge nucleon made of quarks. And these quark stars have different predictions, like this. And in our universe, there's only one equation of state is correct. One of these curves is correct. We don't know which one. And right now, there's some observation limit. We already detected one neutron star with mass of 2, which means everything below this line is ruled out, including these soft equation of states, including these quark star models. They are ruled out. However, we still have plenty of others above this line, including some modified quark models that are above this line. We don't know which one is correct. However, if we do see a FRB following the GRB, then we can probably solve this, because we can use the light curve to measure how long does it take for it to really collapse. And we can roughly estimate what is the spin rate at that collapsing time. And then we can figure out, okay, if it is not spinning, what is the maximum mass? So we can probably find the right curve. However, with the EM signal alone, we cannot do it. We have to use gravitational wave signals. But it is coming. Advanced LIGO, they are claiming that probably in 5 to 10 years, they will be able to detect gravitational waves from double neutron star mergers. If this is the case, then from gravitational wave signals, one can measure chirp mass and this mass ratio. They're both functions of M1 and M2, so the masses of the 2 neutron stars. And with these two, you can probably solve the total mass of the system. Now you know that after this merger, how much mass goes to this supermassive neutron star. And then from GRB and FRB delay collapsing time, you can figure out the maximum mass at that P spin period. And then you can solve, okay, if it is not spinning, what is the maximum mass? This is some speculative calculation, but already if we believe this current plateau is due to this, and we assume some typical masses, 1.4 solar masses, and people already did this. They found that the maximum mass is probably 2.4, 2.5 solar masses. Okay, we need real data to test this, but what I'm saying is, okay, if FRBs are following GRBs, especially after these double neutron star mergers, then one can probably solve this big problem in physics and astrophysics. Okay, the fourth one. This one is related to cosmology. So, so we know that our universe is made of this pie chart. The majority of the content is so-called dark energy, something we don't see, and it's repelling, and the universe is accelerating. And then is a huge amount of dark matter. We do know they're there. We didn't directly see them yet. And then only about 4% of this baryonic matter. However, this 4%, this is called omega B, is baryonic fraction. This parameter has been determined by these methods, Big Bang nucleosynthesis. I don't want to go into details, but based on the abundances of lithium and helium-3 and combine everything together, one can constrain this. And more precise, this determination is from the cosmic microwave background. So the ratio between the first two acoustic peaks, and that can constrain omega B. Some people directly sum of all the baryon matter in the universe, galaxies, clusters, and they found also got something. But these are very nice measurements, especially the second one. However, they are based on models. They are not like directly measure this. If FRB GRB associations are established, one probably can directly measure this. Why is that? Because for every GRB, well, most of the GRBs, you can measure the redshift through the absorption line or the emission line from the host galaxy. So you know where this object is in the universe. The distance we can calculate, we can measure. And then we can also measure this dm. I just said dm is the integral of this free electrons along the line of sight. Then this tells us the baryons, right? So these electrons must be associated with some protons, some baryons. Then we can measure these two independently. From the GRB, we measure Z. From FRB, we measure dm. And then combine these two, one can measure omega b. A lot of cosmological implications, I think in Zhang's paper also discussed this actually. Zhang himself wrote the relevant part, so we are consistent with each other. So basically, the dispersion measure is the Colloquium density. So basically, you integrate over all the free electrons along the line of sight. Unfortunately, this dm includes many terms, so including the contribution from the Milky Way galaxy. So we have free electrons within the Milky Way galaxy. We have contribution from the IGM, intergalactic median. So this is the one we care about. We also have contribution from the host galaxy, that GRB is sitting in his host galaxy. We also have dm inside the GRB. The GRB itself has some free electrons. So we have to properly deduct the other components to figure out this one. Fortunately, so the measured dm is much, much greater than the Milky Way one, right? So Milky Way is pretty much negligible. And host galaxy, we don't know exactly how the host galaxy look like, but our Milky Way is a relatively large galaxy. Let's consider the GRB host galaxy not that too different. Then their contribution probably is negligible too. Then, how about the dm from the GRB itself? So this one needs some calculation, and my student Wei Deng performed this calculation. We calculated for, so basically things like this. So when the FRB happens, because there's a delay of thousands of seconds, the GRB blast wave already goes to somewhere, and this one is moving with near speed of light, because GRBs, they are believed to travel with Lorentz factor more than 100. They're moving very, very fast. And the radio wave is essentially the speed of light. It will try to catch up with this something that's already close to speed of light. So the crossing distance is already far away, because those two speeds are so close to each other. So when the FRB catches up with GRB, the density is already extremely low. Then if you do the integration, it turns out that this dm GRB is small. It's around 1. For the wind models, this is very extreme. We didn't see this such kind of median in the GRB modeling, but we give an extreme parameter, then we can probably give 100. Other than that, it's around 1. It's negligible. So basically, we can say the measured dm is dominated by dm IGM. The other three terms are negligible. If this is the case, then that is great. So we come back to this equation. So the dm in the IGM is mostly contributed by the free electrons in the universe, and then it is related to the omega b. So it tells us how many baryons, what fraction of the entire energy of the universe is composed of baryons. Of course, what we can measure is the fraction of baryons in the IGM. We have baryons in the galaxies, in the stars, but this fraction can be up to 0.8, 0.9. Okay, it's pretty close to omega b already. And then we have to worry about the ionization, because if they're not ionized, the electrons are not free, so we have to consider this ionization fraction of hydrogen and helium. And fortunately, below redshift 6, most hydrogen is ionized, and most helium, first the electron already ionized. So it's essentially you can take this as 1. And then what you have is just omega m, omega lambda, and this omega m and omega lambda. You can use other methods to determine it, and then you can find and measure omega b. So this is what I just said. At z less than 2, both hydrogen and helium are ionized. So these two are 1. And these cosmological parameters, we can rely on CMD, for example, and supernova 1A. We can constrain those, and then we can come back to measure this. This can be directly measured. Okay, I just said, Banista et al., they detected 2 plausible FRB following GRBs. Okay. So could we just perform such kind of exercise? Yes, we could. However, unfortunately, those 2 GRBs are the ones that without redshift. Somehow, I asked my observer friends, somehow, in one case it was the moon constraint or something. It just optical telescope didn't follow up deep enough. But they do have afterglows, but just didn't measure the redshifts. Host galaxy probably is relatively faint. That's unfortunate. However, we have some rough relationship in the GRB based on the gamma ray data. One can roughly estimate the range of the redshift. So this is what we did. So when the redshift above certain value, then it will fall into this band. And then this is the plot. So one can measure this omega b multiplied by f to be lower than a particular value. So these are the allowed region. And you can see that they are consistent with what CMD measured, 0.04. So unfortunately, we don't have real measurements. So we are trying to apply for observational time with Hubble, probably. Try to detect the host galaxies of these 2 guys. And if we detect them, and probably we can use other telescopes to try to measure redshift. We'll see this. But this is encouraging. And then we can kill the 5th one. If we manage to measure omega b this way, then we can go to higher redshift. Okay, so right now we use the low redshift data. Suppose these are 1. Okay, these are all value 1. And then we can measure this. Okay, after we measure this, and then suppose we detect in the future, far future, we detect many GRBs, FRB association, and some of them they are at the redshift greater than 6, 7, 8. Then that would be great. Then this one becomes known, and what you don't know is this one. You can probably map this reionization fraction. So how the universe was reionized, that's a huge problem in the contemporary. So we have these dark ages. We have different models. Some models even predicted the universe was ionized twice. Some of them have smooth transition. Then, if we have GRB, FRB systems, we can map this plot very nicely, and we know which one is the right one. Okay, this is a more extreme. Constraint dark energy equation of state. So there are already 2 papers on this. This is initially I didn't believe this, but when I kill the first 5 birds, and some colleagues said, okay, you can kill the 6. Okay, let's just try it out. The bottom line is, okay. Just now I used the standard lambda CDM model. And in principle, one can put this as the more general. So the dark energy, we don't know whether it's just a standard lambda CDM. It can be one step further. You have W, the W which is not -1, you can other models. Then you can have evolving W, the dark energy model. So one can put this more general form here. And then this time you have to rely on, because at a lower redshift, this is not very sensitive, and you can still measure your omega b. Then your ionization comes into play in a very high redshift, say above 6. Then there it is hopeless. But between this 1 and 6, there's plenty of space. You can probably test this. So this is the type 1a supernova data. You can probably map the universe up to 1 point something, redshift 1 point. However, this is a simulation. For GRBs, we can populate these FRB GRB systems to redshift of 5 to 6. And those are theoretical curves. The middle one, the solid one, is the lambda CDM. W equals -1. And the other two, one is minus 0.8, the other is minus 1.2. So you can see for distance modulus, so this is for the type 1 supernova. So this it's just a matter of how this luminosity distance depends on how sensitive it is on these W values. It turns out to be very close to each other. So it's very difficult to use DL to do this. However, if one uses DM, the main reason is DM is not only the distance, it's the integration over density. And density itself has a steeper dependence on redshift. So that's why when you go to higher and higher redshift, this difference becomes wider. And in principle, you can try to constrain omega m and omega and W here. W is the dark energy equation of state. With FRB alone, probably cannot do that much. However, if you combine this FRB with the type 1a supernova, your contour becomes much, much smaller. So basically, you can use this as a very important tool to constrain this dark energy equation of state.
So is it fair to think of this as a number count cosmology measurement where
Number,
electrons that are the
Yeah.
you're counting?
yeah. Probably I state too much. I'll stop here. I don't know how many birds can actually kill. I'm not saying that I can kill the sevens. Probably I couldn't even kill 1 or 2, because if these associations are not real, then all I said is just some fun jokes.
You are missing the dark matter.
Okay, so hopefully in the future we can have real detections. So I'll leave my conclusions here. This field is very exciting, very new emerging field. And the supermassive neutron star implosion model is an attractive proposal to me. And then within this scenario, one should expect some GRB, FRB associations. We need very rapid radial follow-up to do this. If the associations are confirmed, then okay, so we can study physics, physical magnetic FRB, GRBs, the equation of state, the baryon fraction, the unit of clear energy history, and dark energy. Okay, so if you are interested in, these are my recent papers on this subject. Thank you.
Any questions?
Do I recall correctly, you've only seen 3 or 4 of these?
The FRBs right now, 6, I would
6.
say, not including these 2 associated with GRBs. If these 2 are also real, then maybe 8.
8?
Yeah.
So the first one was observed in 2007. Why only now are we seeing these?
That's a good question. So actually, there are a lot of these guys. Zhang actually knows more about this. So a lot of atmospheric or terrestrial related high dispersion pulses. The problem is not to say, okay, we only detect these 4. The problem is how can we are sure that these 4 are not those guys, the nearby abundant ones. That's why they have been very careful. They have to use, for example, the frequency-dependent profile, arrival time. The profile itself also carries a lot of information. Yeah, so that's why they only they reported those 4 actually a couple of years later.
Coming back to that, the dispersion measure, when you plotted the picture of it, it looks very much like the chirp you would actually expect. We have an experiment looking for cosmic rays.
Right.
where it's a bistatic radar. You have a radio at some frequency, and it bounces off the moving front of the cosmic ray, and that gives you a chirp that you're seeing. Is that not a possible explanation here, or why not, actually?
I'm not an expert on this, but actually in Zhang's paper have a lot of discussion. Those guys are called
No, so in fact, I checked this cosmology once. Seems the time scale does not match.
I was thinking it was too long. It's,
yeah,
it's many milliseconds, right? As opposed to a few microseconds.
Right.
yeah. So yeah, basically they try to rule out those possibilities and say that these guys are looks like real ones.
So thinking about other extragalactic radio sources, and I know the timescales may be hard to match, but are there models where AGN plays some role in this in terms of, I don't know, like localized magnetic reconnection and accretion disks or jets or some things of that sort?
Yeah, that could be one more model. I think naively the time scale does not work, but you said it can be some local region. And also there are no AGN association with these four, because Avilo found one flaring star, and they say, okay, there's a flaring star association. If somebody see an AGN nearby, must a paper come out, but so far, no.
It seems like the spectrum